right. There's a lull in the crowd noise, so I guess that means it's time to introduce Michael. Um, so I think everybody knows Michael, right? He's our Associate Dean for Research. Really excited that we were able to that the timing worked out for this particular talk. There was just an opening in our schedule, and Michael's doing really, really interesting work on, as you can see from his title, on essentially the interplay between water, environment, economics, and energy, which is, of course, a pretty relevant topic these days. Just to give a brief introduction to Michael, aside from being a really kind of a badass cyclist who's ridden like 500 miles in 24 hours in Death Valley and things like that, that's sort of his side gig. But he's also a really accomplished scientist and had a bunch of leadership positions. And so I'm just going to go through briefly. I don't want to embarrass you too much, Michael, but so he has a bachelor's from Hartwick College, which is in New York. It's a beautiful place. I didn't realize this, but if you've not been there, it's a great place this time of year in particular to see beautiful leaves. Something that if you grew up in Texas, you don't know what I'm talking about. But if you grew up in the northern half of the US, you do. Then got a master's degree from Ohio University and a PhD in soil and water science from the University of Arizona, which is like one of the powerhouse places for hydrogeology and hydrology research. He then spent some time as a research professor at Georgia Tech, and then for quite a while at the Desert Research Institute in Nevada, where he had a series of leadership roles there. And then in 2010, he joined the BEG, and again has taken on the mantle of leadership in a bunch of different ways. He maybe most importantly was on the search committee for the director of the Institute for Geophysics about 6 years ago, which is pretty important, right? So. For those of you on Zoom, you can see me laughing and you can see everybody in the room rolling their eyes. And then over the past few years, he's been our associate dean for research and has really helped to facilitate a lot of things at the college level for the Jackson School and then connecting us to the broader university. Of relevance to this talk, for those who don't know, he actually just delivered this talk a mere few days ago at the Geological Society of America. This was a named lecture, the Halbudi Lecture, so it's kind of a big deal and a plenary lecture that he was selected to give. And so we're really fortunate to get our own private version of this of that talk that was given at a national meeting just a few days ago. So Michael, welcome and thanks for joining us.
Thank you. Can you hear me? Is my mic on? I try to avoid hot mic moments. Well, thanks a lot to everybody being here and spending a couple of minutes. I did give the talk in San Antonio a couple of days ago, and so I'm really glad to be able to do it here. We've been working on this project for quite a few years, and it's hard to find the right venue to give it. So it was a little bit of a trip, actually being up there with a teleprompter. I don't know if anybody has ever given a talk at the podium in front of a teleprompter. It's very trippy, but interesting. And so anyway, this talk is probably outside of most geophysics topics that you all are involved in day to day. And so what I'm going to do toward the end is I'm going to try to bring it back into where geosciences is. Even the people at GSA are probably like, why is this guy blathering on about electricity and cost for electricity? I'm a geologist. And so I actually show here's where geology fits into this entire supply chain and value chain of knowledge that in a topic that is in the news basically every day, all the time. And it's a big topic of discussion in terms of critical materials and this whole question of how are we going to generate electricity going forward, and what does this mean if we're going to transition the electricity generating sources. I do want to thank my co-authors, Johnny Das, who is right here, right square in the center of the room, the gravitational pull, and Gurjan Gulen, who's an economist who has been working at the Bureau for longer than I have in various positions, and so he's an amazing energy economist. And so I'll kind of talk a little bit about some of the stuff that the team has been putting together. And so let's see if I can get this to go forward. Okay, so why are we motivated to do this? It's a little bit outside of most geosciences. And probably because I have ADHD, I just get interested in stuff and then I chase them around like squirrels until I'm satisfied that I know enough about it. And so we just kind of start off, there's a significant earth material processing needs over the rest of the century, which, 75 years long between now and the end of the century, when we're really is in many cases, it was the goal of decarbonizing generation between, throughout the 21st century. And, but at the same time, we have all these trade-offs that we have to deal with and we have to address from a societal standpoint, from a policy standpoint, and from the reality of what it's going to take to change this generating source from combustion-based to, I would say, low carbon-based. We have, on the one hand, we have to mitigate climate change. We have to preserve environmental quality, and we have to make sure to provide reliable electricity to communities at a price they can afford. And we scale that up to 8 billion people, which is our 8-point-something billion right now in the world. And where the reliable and affordable comes in is that the moment these lights go out is the moment you stop thinking about CO2. Right? We have to have the case number one. The first thing we have to do is make sure that we have the lights on. So once we can do that and we can protect our families and we can protect the things that we value, then we can start thinking about CO2 and things of that nature. But we have to have that first. And so we're kind of going under this, our group has always been focusing on making sure that we have a multi-criteria that we're trying to balance. If we're only interested in one, if we're only interested in generating electricity, and we just don't care about anything else, well, then, it's going to be a bad outcome. So we have to balance all of these. And that's really what we're trying to do. We're trying to do it by using life cycle assessment and economic principles. We're looking at global supply chains of critical materials that are currently being used and incorporated into the infrastructure that's being built and being deployed. We'll talk a lot about that. And we're looking at the expansion into mid-century of what we expect in Texas, outside of data centers, right? So we'll put data centers aside, we'll talk about that. But our estimates are without the 50 gigawatts of data center expectations that are going to be between now and actually 2033. Who knows what 2050 is going to be like? That's going to be wild. And so that's kind of how we're going to go about doing it. This project has had a wide variety of different backgrounds. So all the students and the interns are on the right, all the researchers are on the left. And it was this mishmash of mechanical engineering and systems engineering and electrical and chemical and energy economics. And it took about a year for us just to harmonize ontology. Like, what does it mean for an energy geologist or an energy geoscientist when you use the word sustainability? What does it mean for an economist, or what does it mean for an environmental geoscientist? Right? And so we're just working on just getting the vocabulary correct, because they usually mean different things in different fields. But there's been an amazing group of people to work with, and it's been super fun to be able to do that. So let me start off with just a definition of life cycle assessment for those that are unsure of it. This LCA is essentially it's now an internationally standardized approach for assessing environmental impacts associated with a product or process. It was started in the 1970s by an engineer at Coca-Cola who just asked the basic question: what, from a bottle standpoint, is glass, plastic, or aluminum more or less environmentally friendly than the other choices? Like, how would you think through this, so that from a conservation standpoint, and how would you go about doing that, all the way from where you mine, the bauxite to get aluminum, where you have the silica for the glass and the carbon for the plastic, and how do you go through that entire process? And so we're doing all of that for these energy sources. And all life cycle assessment studies have this little dashed box around there, and that's known as the system boundaries. And our boundaries are from cradle to grave. You can see that on the bottom, and on the top, these are the various steps in what that life cycle is, all the way from the mine and the location where we mine the materials. This is right, here's the cobalt and the nickel, and here's the lithium that's being mined, and they go all the way to the processing and refining of the material to incorporation into a product, The product is deployed somewhere in Texas, and then it generates electricity or is involved in generating electricity for the next 30 years, and then we do something to dispose of it, or we recycle it, or we send it to the landfill. I mean, what do we do with this material? We include all of this. Pretty much from start to finish. We have all the transportation pathways. You see the little boats there and the little dump trucks. So we do the transportation wherever if the cobalt is mined in the Congo, okay, in the DRC, where does it go? Well, it gets put on a truck and driven all the way across the continent of Africa to Tanzania, put on a boat, shipped over to China, where it's refined, and then put into a battery and sent back over to the US. In some cases, we have some materials that travel 40,000 kilometers before it's actually deployed in Texas. So it's just a huge global Gordian knot we're trying to deal with. But we try to take each one of these as various stages. And so here's our general research approach. So one of the what we tried to do is we could do an LCA study for every type of electricity generating system, all the way from geothermal to nuclear to coal to gas and so on. We chose the ones that are really top of mind and that are more likely to be deployed as we think about decarbonizing. So in phase one, we do a side-by-side study of gas, wind, and solar with and without batteries, all generating the same amount of electricity. So in other words, a 500 megawatt gas plant that operates at 70% of the time, which is what's known as the capacity factor, generates 3 terawatt hours a year. It's enough for about 285,000 homes. We then say, how much solar do we need to deploy to get the same amount of electricity? Because the grid doesn't care about the capacity of the plant, it only cares about what it can generate. And so we would need about 1.3 gigawatts of solar to match the same amount of electricity generation that a 500 megawatt plant, a 0.5 gigawatt plant would be able to generate. So it's about a 2.5x to almost a 3x difference in capacity. Same with wind. Wind's about 2x. Because the capacity factor is different between these systems. So we do this side by side, all of them. I'll show you all the results. Then we take these individual plants that we're doing side by side, and we connect them all up to the ERCOT grid. We have every substation, every major power line, every generating station, whether it's wind, solar, gas, nuclear, coal, so on, and we put it into a grid dispatch model. It's known as a cost production model, and we model the distribution of the electrons and all the load centers, where the people are using it in Dallas, Houston, RGV, San Antonio, that whole area, so that we can basically track the supply and demand of electricity on a minute-by-minute basis or an hour-by-hour basis for every plant in the state of Texas. And because we're doing each one of these plants individually, and we know what the impact is of the plants individually, we can track the environmental cost to generate electricity of every plant in the state of Texas every hour. So it's an enormous data set, super fun. You like big data. We do. Then we look at what is the cost to generate it. We're going to talk a bunch about some of the economics here. And we have not only the cost to generate, because it costs a certain amount to get the gas from the wellhead to the plant. It takes a certain amount for nuclear and for coal. There's it's basically free energy to get wind and solar, so there's no fuel cycle cost there. But for all the others, there's a fuel cost. But we look at the environmental impacts of every one of those megawatts, like what's the effect of things like PM 2.5, and how much ecotoxicity, and what's the CO2 emissions, what's the amount of water that's being used in each one of these plants every hour. And so that's kind of the whole arc of the project, and we're at the tail end of the arc. And now we're just writing up papers, and we were talking to people at Cambridge, and they're like, "Oh, we want you to write a book." I'm like, okay. And so this is the system boundary for combined cycle gas turbines, CCGT. You'll see this throughout the talk, all the way to where the well pads are and the well casings and the amount of water that's injected, the 20 million gallons of water that's injected every time we frack a well, 20 million pounds of sand, we include that. We include the pipelines that go from the well all the way to where the gas plant is. We drill 22 wells and frack 22 wells a year. Every year the plant is operating in order to generate the 3 terawatt hours from that one plant. So it's 22 wells a year, giving decline curves in the Permian. So we studied the decline curves and how quickly these wells are gonna basically peter out. We have the processing, we have the transmission lines, the storage, the plant construction and the operation, all the way through to the point where we go to electricity on the bottom and the emissions off to the right. We do that for all the plants. And we do that, we have the same for batteries, we have the same system boundaries for wind and solar and so on. And in a typical LCA study, there are what are known as impact pathways. There are 16 impact pathways using the Recipe 2016 method that is pretty much the national or global standard that people are using. And I don't know if you can see it. Hopefully I don't mess it up. Okay, so here's particulate matter, PMPF, ozone formation, ionizing radiation, stratospheric ozone depletion. There's a whole bunch of ecotoxicity. There's land occupation, there's water use, CO2 emissions, and so on. This is essentially part of the standard approach that's used in LCA. Now, in order to really make these intercomparable, because these are really hard to compare, some of these are in kilos, some of these are in cubic meters, and so on, we basically try to divide everything out by megawatt hours of generation, just to kind of normalize all of the impacts into one metric that we would then be able to sort of take a look at. And without doing that, the numbers are sort of floating, and there's no standardized way of looking at it. And you can imagine that having 3 or 4 or 5 or 6 different electricity generating sources over a period of 30 years with 16 different impacts, it's 30 times 5 times 16. The number gets big. And so rather than preventing you from screaming, running from the room, we're really going to look at the 4 here. We have the results from all of them, but we'll look at particulate matter formation because PM 2.5 is a significant impact to respiratory and pulmonary function. And so that's a really an important one. We'll look at global warming potential, which is GWP, which is CO2 equivalent emissions. That includes the entire methane and the carbon chains from propane, decane, all the way down to methane, and what effect that has. We'll look at water use in cubic meters, and we'll look at land occupation and transformation, because these are things that we see every day. And of course, CO2 emissions is in the news all the time. And right now, people are really talking about water because of data centers. And so those are the ones that we'll kind of look at here. These are the studies we've done to date. On the left are critical materials, nickel, cobalt, lithium. We've published the cobalt and the lithium so far. The nickel is we're gonna basically resubmit it. We sent it to ES&T, and they said, well, we already know about nickel, so send it somewhere else. So we'll do that. We do these energy systems, CCGT, wind, solar, battery storage with some CCUS or carbon capture. And then we look at all these life cycle phases. The paper on reuse came out on Wednesday, so I could change the circle. And so these studies are very place-based because where the generating unit is located matters in terms of the transportation distance from where the gas is being produced and extracted. So we're looking in West Texas. These blue bubbles are wind fields, and the yellow bubbles are solar. These numbers change quite a bit, and for people that are tracking this, there's this huge churn over at ERCOT on when projects are being submitted to be interconnected to the grid, when they're being pulled back, if they're being funded, and so on. It's pretty messy. And on the right side of that box is known as the McCamey CREZ. It's basically a substation, and all the power lines for the CREZ lines go through this one area. And there's so much congestion over there. They don't have enough power lines to move the solar and wind that there's just a lot of curtailment and line congestion. So many of these newer projects are being moved to the east of the CREZ line so that they can essentially have a shorter distance to the load centers in Dallas and Houston and so But in any case, we try to keep ours kind of right in the center of this area. So this is what the results look like, and this is all the way from the manufacturing and the mining of the material all the way to the end of life, as I mentioned before. On the top left is particulate matter formation. The bars on the left, the blue bar is combined cycle gas, and then you have CCGT plus gas capture, CO2 captured, and then we have wind and solar, and then we add the batteries. So you can see that the combustion based over the long period of time basically has a larger PM 2.5 emission spectrum, and you can see here again everything is essentially subdivided or divided out by a megawatt hour. So we're normalizing it based on what's actually being generated at the site. If you look at global warming potential, CO2 equivalents about 470 kilograms per megawatt hour of CO2 is emitted. It's about half a ton per megawatt hour. So these are very common. These are right in the range of what is being published typically today in terms of generation. We still have some CO2 that's emitted even with gas capture because we have to run the plant. And in order to run the plant, there's a 30% parasitical load on to run a capture unit. You have to actually generate that much more electricity, which means we have to drill that many more wells. So we have to drill another 7 wells to run the capture unit, and there's methane being emitted, and there's diesel that runs the frac job, and so that's where that CO2 is coming from. But when you look at wind and solar with batteries, pretty low because it's basically zero CO2 emitted during operation. So it's about a 20x difference in CO2. Land use potential is the highest for solar, which is not surprising because solar is the lowest energy density of the 3. So it requires that much more area. And it's blanketed out in a large areas. It's about 5 acres per megawatt. So for a gigawatt, it's 1,000 megawatts. It's about 5,000 acres per gigawatt of land that's taken, and that's just for the support area for the panels. So if you scale this thing up into the multi-gigawatts, it's a lot of land, probably in the million acre plus. And then the water consumption here, we can see this is 1.35 cubic meters per megawatt. That's about 2/3 of that is to cool the plant. It's about 0.7 cubic meters to wet cool the power plant, and the rest of it is for hydraulic fracturing to get the gas. And then we have a little bit more for the water, and again, it scales up if we want to do the CCGT, and then it's a fairly water intensive process to make the solar panels and the batteries. So those are kinds of the numbers that we're seeing. For the plants that are essentially not connected to a system, it's just a side-by-side based on generation. If we look at this over time, and so the x-axis is time, it goes out to 30 years. That was sort of our lifespan. The thing that you'll find, and I'll kind of go through these a little bit quickly, but you see that there's an immediate penalty when it comes to particulate matter for the intermittent sources, for wind and solar, because we have to a lot of processing of the mined materials in order to get the cobalt and the nickel and the glass and everything, the copper that goes into the panels. But eventually, over time, the combustion based has a higher value because this is occurring while the electricity is being generated, whereas the intermittent sources, it's being generated prior, the CO2 or rather particulate is being emitted before we start generating any electricity. And here it is, if we were to, when we normalize it by megawatt hour, and it's really after 30 years, it's about 90 terawatt hours of generation. And this is just an example that no matter how big the number is, if you divide it by infinity, you get to 0. Same thing for CO2. There's an initial CO2 penalty that has to be essentially overcome. This is on the left-hand side, so it's a fairly energy or CO2 intensive process to build all this material, but eventually it's basically exceeded by, the emissions from the combustion plant. Same thing that you can see over here. That's about 468 is that long-term line over there. And I'll just kind of go through, this is for water. There's a water penalty because it requires a fair amount of water to build the solar. But then once the solar is built, there's really not that much more that you need except to occasionally wash wash the plant and or wash the panel surfaces and things like that. And same with land. Lots of land is needed for solar. Less is needed for wind. And the combustion is the least because it's the densest fuel source. If we were to go ahead and just look at all of them together in one bar chart, and so any of the bars that are below the zero line relative to gas is essentially an improvement, which is lower emissions if you're below the line, and it's higher emissions if you're above the line. And so we kind of talked about some of these already. The PM 2.5 is slightly below. The CO2 is significantly below. And then you have the land and the water. And all of these that are above the line are typically based on either eutrophication, which is nitrogen dry fall, or it's ecotoxicity. And we're going to talk a little bit more about ecotoxicity, which is essentially chrome-6, lead, 2,4-dichlorobenzene, and a wide spectrum of potential chemicals that are released during combustion and during the processing of materials that are being used to generate electricity. But this, we studied this a lot, and it's very confusing to look at ecotox because it has this significant outsized influence on the cost, because even small amounts of lead has a huge impact to the environment and to human health. And so the cost of that, from an economic cost, is just overwhelms everything else, overwhelms CO2 by orders of magnitude. So it's a challenge to think about how should we be thinking about this, and also the metals, they never break down, right? So if you put chrome-6 in the environment, it's in the environment, and lead basically forever. The CO2 at least has some decay with time. Okay, so what are some of the high-level observations here? That there are going to be some trade-offs. We see some impacts are higher, some impacts are lower. So there's a reality that we have, that there's no perfect technology. Some of these are going to be positive in certain ways, and this allows us to actually choose the technologies to generate electricity based on the goals that we set as a society. Most of the impacts are borne by host communities in other countries, because the mine sites are in the Congo, they're in Indonesia, they're elsewhere, and the processing plants are almost all in China. So what we're really doing is, and to some extent, we're essentially offshoring the environmental impact that's being borne by communities outside of the United States. And we just have to accept that and say, okay, well, all right, that's a price we're willing to pay. And at the other communities, they also have economic value by having an opportunity to do some work over there too. So it's really, from an ethics standpoint, it's an interesting ethical problem. We did not study this part of it. We're just looking at the data. We don't want to get into the ethics part. For many technologies, we're front loading the environmental impact, but then the fuel cycle itself is impact free for the most part. And that over time, the OpEx, the operational expenditures tend to really exceed. So if you can keep your OpEx low, then the environmental impacts are low also over time. Okay, so now we're going to go ahead and we're going to do this for the state of Texas. And for those that are unaware, ERCOT is its own system, right? We are not connected up to the national grid. It's what allowed Texas to change its electricity generating sources faster than any state in the country, which there's some level of irony there. And so anyway, this services about 90% of the state of Texas. And it allows us to essentially study an island in the middle of the country. We could not do a study like this in Iowa or in New Mexico or anywhere else, because they have porous boundaries, and it's really hard to do a systems model when your boundaries are porous. These are no flow boundaries. So we can actually study this as an island, which allows us to run a study like this. It's very fortunate for us. And it's why we chose our home to do it. And so these are the ERCOT load zones. So ERCOT breaks up the state into the west, into the north, into the south, into the Houston area. There's Austin Energy, which is right there right here. If I can get this right there is Austin Energy, because we have our own essentially a monopoly in the middle of Texas. And these are the power lines. And so this is known as a critical energy infrastructure information. It's national security level data that we had to get security clearance to access. And then we had to put it on a computer that was like so secure. It's in a locked room. It's not connected to the internet. And the only person that can see it is Johnny. And she's the only person that uses the data. And nobody else can even get to the computer. Because I would certainly muck it up if I tried to do the model. But we're using all of the power lines that are essentially part of the national security data set. And we have, we hired early on, we hired a consultant who does work for ERCOT, and this is his job. He does grid modeling every day. And on the left are these are the three different grid mixes over the next 30 years or so, 25 years. On the left is known as current trends. Current trends is what ERCOT expects between now and basically 2037. They go out 15 years. We just extrapolated the trends out to mid-century. So every 5 years we change the grid mix based on what ERCOT expects every 5 years. We just interpolate so that we can get a smooth curve. And then we basically push higher wind and solar. This is what we call HWS, higher wind and solar. And then we have higher dispatchable. So here are the actual generation percentages that we ended up with at 2050. So, the ERCOT expects about 30% wind, 17% solar. I'll show you how close they are. 44% CCGT and 5% nuclear. The rest is basically in decimal points. Most of the coal plants retire out. And so we're really, the numbers may not add up to 100, but it's pretty close. The second one, the 40% wind and 24% solar, we started at 75%. And the grid kept collapsing every time we tried it. We even used batteries that don't currently exist as a way of stabilizing the grid. We always had about 15% on unserved hours. So when ERCOT says unserved hours, that's a euphemism for blackout. And 15% blackout in the state of Texas is over 1,000 hours a year, blackouts. You just imagine the outcry if that was to happen. We simply can't accept that. Now, if we continue to back down that percentage and backfill with CCGT, we had, I think it was 0.1% unserved hours, which is like, I don't know, 8.7 hours over a year. Okay, we can deal with that. We can load shed the rest of that, so we're okay. And then, of course, the higher wind and solar, we assume that we were able to build some more nuclear power plants, and we would be able to backfill the growth in ERCOT with some with nuclear and some with wind and solar. So those were the grids, and just to give you a sense, I did a screen cap for anybody that's into this stuff. ERCOT has an app. It's very data rich, and you can download it while we're talking. You can see this was taken in 9/16. I was actually in a meeting with Demian when I hit the screen cap, and just plopped it into this talk moments before coming here. And there's the mix: 12.2% solar, 33% wind. That's the actual generation mix at 9/16. And the reason that becomes important is if you go outside, you'll see, okay, first of all, it's pretty cloudy. Most of West Texas is in rain. And the front is coming through, and we're going to have that front hit later today. So the wind is kicking up really well, and the solar is basically, it's cloudy, so we're not generating that much. That's just the reality of what's in the grid right now. Now, typically, we're over 50%. In some cases, we're at 2/3 intermittent, 2/3 wind and solar during the day. Is common in Texas, which is great, because it's 2/3 of the grid is basically fuel cycle cost free and CO2 emission free. And my economist and I, we battle back and forth a little bit about the value of that, and okay, the risks and so on. And everybody talks about the risks of overbuilding wind and solar. Got it, but still, that's pretty cool. And then you could see coal and lignite is 12% and 7% for nuclear. So anyway, I thought that was pretty cool. And so when we do a systems impact and we compare the current trends versus that higher wind and solar. So what we're doing is we're doing everything relative to higher wind and solar, because that's what we were basically really pushing to decarbonize the grid. So the bars above the line is the impact is higher than if we have higher wind and solar, and those below the line are lower. So higher here by cranking up more wind and solar, we're reducing environmental impact. Those are the bars below the 0 mark. And you can see, you know, there's global warming potential. It's about a 25%, 30% savings in CO2 at the system level. There's less water because there's less cooling. There is, in some cases, there's more land use because we have more that higher wind and solar has more wind and solar than it does for combustion based and so on. And you can also see the impacts also of this, of the ecotoxicity. There's human carcinogenic toxicity and non-carcinogenic toxicity, marine eutrophication, and things like that, that are all, again, based mostly in countries outside the United States. And so we were like, wow, you know, I mean, we can go ahead and do, you know, we can do draw a straight line with 3 points and come up with a kind of a crummy R squared, but we didn't want to do that. So what we decided to do was to take the model and sequentially and slowly ramp up wind alone and solar alone to see how small changes in the fleet would change the environmental impacts one parameter at a time. Because this is a hugely unconstrained model with thousands of parameters. And when you're trying to optimize thousands of parameters, we all know that we have an ill-posed problem, and, you know, we could come up with infinite solutions and all the rest of the mathematical outcomes. So what we want to do is simply change wind at the expense of gas, one step at a time, ranging from 25 to 39% of capacity. CCGT drops from 1/3 to 20% and so on. And then we would be able to plot the environmental impacts just one step at a time by changing one parameter, just to see, well, how does this change as we get closer and closer to that point where we start getting an instability in the grid. And so we did the same thing for wind. We did the same thing for solar on the right. So that's case 2. And so these dots here show the difference. So PM 2.5 goes up pretty dramatically as we increase the amount of solar. That's because we have to build that much more solar in order to generate that much more electricity. On the right-hand side, CO2 continues to decrease. So if we increase wind, that's the blue here, we go from, remember, it was a 468 just for the CCGT plant. When you connect all these things up to a system, now the CO2 emission at best is 245 per megawatt hour. So we can kind of start to compare all of these things together. Big drop in water consumption potential, not so much for solar because it takes a lot of water to build the solar panels, and we're simply offsetting the water use in Texas to cool the plant versus the water use in China to build them. Do we care about that? That's up to you. And it's the same thing with land occupation, right? So we're basically we're reducing the amount of drill pads that are needed to operate and to get the wells to operate the plant, but we're replacing that by blading more land in order to get the panels. So it's a trade-off. The other thing to note is that even with the highest amount of solar, we still don't generate the same amount of electricity as we do for wind. So there's a gap. And that's because wind is more dense of an energy fuel than solar. Solar is the least dense energy source. And so we see that here with that gap between them. Okay, so what are the costs? So for years, Lazard, which is a consulting firm, has been issuing what's known as the levelized cost of electricity, LCOE. And most people who are in this business realize that is the most easy metric in the world to create bias from, right? Because LCOE only is the generation of the electricity itself at the plant. And wind and solar is basically fuel cycle free. So it has the lowest LCOE. So the people that love wind and solar say, see, it's the cheapest. And the people who love oil and gas, they say it's the most expensive, and here's why. And so we're like, well, okay, let's come up with our own metric that basically includes all of the other costs that are necessary to essentially connect wind and solar up to the grid. And let's compare that to all the rest of the fuel cycle and the combustion base so that we're essentially comparing apples to apples, because otherwise we're not. And so on the right-hand side, the CCOE, the consumer cost of electricity, this is what you pay from your bill. And you get your bill from Austin Electric, and you'll be able to see, okay, what am I paying? You'll say paying 12 cents a kilowatt hour, but I'm also paying integration costs and line costs and curtailment costs. And you see all these other things that are on your electrical bill. I don't know how many people check their electrical bill to say, oh, how many kilowatt hours did I use this month? I'm about 600 without my kiln. And so, okay, it's about 12 cents plus all these other fees that you're all paying, but they're being hidden. So it's really not transparent. And I would say it's not quite lying, but it's not honest. So here we include all of these costs. Backup costs, that's batteries. Congestion cost, that's line congestion I was talking about before, that all those electricity going into the McCamey-Cres, they're getting curtailed, which means on the other side of the McCamey-Cres in East Texas and Central Texas, you have to fire up more gas plants in order to make up the difference of the electricity that was curtailed in West Texas. So again, these things, supply and demand has to be matched minute by minute. There cannot be a period of time where there's more demand than supply, because the grid will collapse. It's an incredibly complex system. So we include that, transmission costs, load loss, this is load shed events, things like that. So we include all of those. And that's just like an explanation. And so the way that you take those integration costs and how you apply them across the different technologies matters a lot. So, so we have 8 clusters for each different generation source. Okay, so here's the basically the current trends in the higher wind and solar, and for nuclear. And as you go all the way across, you can see on the bottom the brown bar is all the way to the right, and the dark blue is all the way to the left. And the way that we integrate those costs changes what it is in 2023 dollars per megawatt hour. In some cases, suddenly the generated electricity is over $100 a megawatt hour. I'll show what it was when I showed that graphic before. And so this is kind of a little bit of a confusing graph. So if we just show just the wind and solar, because that's where most of the growth in generation is going to be occurring in Texas. And if we look just at the solar, so that bar right there is if we apply all the integration costs for that for the solar side just to on the wind, if we include all that to solar, so we're going from about 50-something dollars to 110. If we take all of the integration costs of line congestion and load shed and all of those go into solar, solar now costs over $100 a megawatt hour. If we do it, if we scale it based on, and we weight it based on the amount of generation of each unit, now we're down in the $70 range per megawatt hour to generate electricity. So it matters a lot. I mean, when you see the difference here, these are big, big numbers, and these are eventually going to be paid by us. And so this was the cost, just to give you a comparison. At 9:16 this morning, it was $23.48 was the wholesale price to generate the electricity. All those other costs are things that are being added onto our bill that we all pay. And for people that are on the lower end of the socioeconomic spectrum, that becomes a higher and higher bite every time those numbers go up. Germany, by the way, is very expensive. I think it's hard to get the exact numbers, but it was probably 3 or 4 times that. So they're now dealing with this, and most of Europe is dealing with this in some cases. And about 6 months or a year ago, Spain went dark because they overbuilt solar and the system wobbled, and then the whole system tripped, and the whole country went dark for 8 hours as they tried to rebuild the grid. So they overbuilt too fast. So there's a cost to overdoing that. So one of the things we've been trying to do, and this graph is we're trying to take, here's the cost to generate the electricity, and here's the cost of the impacts of building out and generating electricity as well, the environmental costs. So on the left side, I was talking before about ecotox. Here's the terrestrial ecotoxicity potential, TETP. It's 50 cents a kilogram of 2,4-dichlorobenzene equivalents. That's the low end of a meta study that was done by Arendt and others. There's so few of these studies that there were 9 studies done total. So this is the statistics of small numbers. Every one of them has different system boundaries and different assumptions and things like that. So if we take the assumption that we have very, very low numbers here, low numbers of studies that Aaron did, we look at just the minimum cost estimates. On the left, somewhere on the order of about $500 per megawatt is what's basically the environmental cost of building out the batteries. right, on the low end. And you can see on the right, if we just remove the ecotox and we just make a graph without the ecotox, it just overwhelms everything. We really can't see, any of the nuance. So on the right side, we remove the ecotox, and now the numbers drop down to about 100. And I'm showing them relative to what the cost is to operate the grid. And so this represents basically an environmental surcharge on the cost to us, because it's our environment that's being impacted. Remember, there's no environmentally cost-free generation anywhere. Coal is the highest, so it almost doubles the cost of coal. If the CCOE, the cost of electricity, is only, say, $35, well, we just doubled it because of the environmental impacts. That would take it up to one of the most expensive electricity costs, right? And the same thing, battery is very expensive, but it has no environmental surcharge to speak of. I thought it was interesting. And these are the numbers. The GWP is 8.25. It's about $8 a ton, right? So these are things that we toss the social cost of carbon, those numbers around a lot. We look at these. If we were to go ahead and run this with the median costs from Aaron, the social cost of carbon goes up to $93. Remember, typical, depending on the administration, it's anywhere between $8 and $200. Somewhere in the middle is what we use. And it increases the cost of coal from what it was $35 to over $400 per megawatt hour. So the environmental cost as an add-on to the cost of the grid itself is super high, right? And in some cases, it's still a relatively moderate environmental surcharge to run wind, solar, and batteries, which I think, again, is interesting outside of this ridiculously high ecotox number of over $10,000 a megawatt hour to run the batteries. So, these are really challenging numbers to try to kind of get across. Okay, so what are the takeaways? And, hopefully there's some, appreciation for the need to sort of balance all of these things. We have to have a reliable grid. The model forces reliability. It also forces low costs. So it uses the cheapest electricity cost. And we have to balance that with low environmental costs, because there's a cost to us in our health and, in the beauty of the environment and things like that. The emissions are heterogeneous in space and time. We see many of these impacts are going to be felt in other countries. Some of it's front loaded, some of it's occurring all the time. It varies. And so we have a really, really rich data set that we can look at and start thinking about how, if there was going to be a policy change, what would we want that policy to do? What would be the goal here? Is it really the mining that's the highest CO2 emission? Well, if that's the case, we need to electrify the mining fleet. We need to put really big batteries in those dump trucks so that that whole sector no longer generates CO2, because we've shown that it's currently one of the highest sources of electricity of CO2. CO2 is only part of the story. There's a whole variety of other things that depends on what we value the most from a society standpoint, economic standpoint. Those things become important. And then we really need to understand the environmental economics of all of this. These numbers are pretty squishy. There's a whole field of environmental economics. I don't know that it's nowhere near as rock solid, no pun intended, as geophysics, which is like it is or it is not. You gotta love R squared. These numbers are difficult to pin down, which means that it's difficult for the public to understand them. So the more work we do on that, the better. So where does geoscience fit into this? I did this a couple days ago. These are the GSA divisions: economic geology, energy geology, environmental and engineering, hydro, geomorph, soils, geo and society. There's many, many areas that we as geoscientists, that the Jackson School should be involved in and could be involved in, all the way, not so much on the processing, but but definitely on the manufacturing, on the operations, and so on. So many things that we could be doing from an environmental geoscience standpoint, and I think we are. And if we look just at this, you saw that it's at the beginning. So I color coded them. In some cases, I got stylish and I have like multiple colors. I didn't know how to do that before. And land resilience, ecosystem health, human health. These are all the areas that many of us work on already that we can now start to apply to help solve this problem. It's this and water supply and air quality are probably the most important things that we, from a mission standpoint, that we could tackle. And I guess we should tackle it. And so anyway, I'll stop there, and there's time for questions. I don't know where the box is, but I want to throw it around because it's fun. And I'm happy to take any questions.
Thanks, Michael. There's some time for questions.
Start to get nervous when we was approaching. I'm gonna miss it. I'm gonna miss it. Incredible work. Congratulations. And Danny, great work. This is my passion, and I'm really impressed. And had a bunch of questions that you were clarifying during your presentation, but at the end, I have this feeling that deeper you get into this, more questions. So, how could you advise regulators, because this has to do a lot with regulators, with so many questions and so many trade-offs, to make a right decision? Because did you get to the point to get the best solution for like the energy planning and development of ERCOTs?
We didn't.
Yeah.
So there's a couple questions in there. So if we had infinite time, the typical, like when we really push the grid, it takes over 30 hours to finish the model. The model itself costs $100,000 to get the site license, and we ran out of time basically. But we pushed that computer like hell. Poor Johnny was seeing stars. Because we knew we were in limited time. We just went one after bang, 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 as fast as we could to generate as much data as we could. And so we didn't optimize all three because we could run all this into an optimization scheme. The models themselves are not designed to do this. And it's different than if we're using Lemberg-Marquardt or simulated annealing or something where we're trying to come up with a parameter set. But we have thousands and thousands of parameters in here. So it's really, really hard to do that. Where you place, we ran a data center job where we put the data center next to Dallas, and the model completely crashed. When we ran the model, when we put the data center in West Texas near the wind field, it simulated in 30 minutes. So it depends a lot on the position and the size of the plant as well, which means that you now have almost an infinite combination of parameter space. So if I was to, we didn't do that, but I think that in the end, that middle high wind and solar comes pretty close, right? And that's actually where we're headed to right now, in some ways. And we're seeing this typically from a generation standpoint. If I was to advise policymakers, I would ask them to ask the right questions. And I think that we have a difficult time as a society asking the right questions. We tend to narrow the questions down so that it's easy for the general population to understand. But these are not, if we ask this simple question, okay, the only thing that we care about is low cost to the consumer. Well, okay, then there's going to be a cost. We're going to see what that cost is. That is not being incorporated into. So we have to ask the right questions. That's what I would suggest to start off.
Yeah, just where are you locating these additional solar generation? Because that and that will impact.
When we expand out when we expand the plants, we are expanding them in areas where current plants exist today. So we're not suddenly complicating the situation even more by pushing the plants in new areas. If we ever get that geothermal money, we'll be able to do that in geothermal, but it'll be difficult to do when we're talking about 60 to 70 gigawatts of solar, which we expect in the grid going forward.
Where are you?
It was a great toss. Really fantastic. Okay, one comment, which is just, I find that it's so fascinating and so worth doing to try to put a cost on everything so that you can do this normalization procedure. And then like if I was reviewing the book, I would say it's a little bit of a cop out to say like, well, we can't do that with ethics. We can't think about some of these ethical considerations. I feel like it could be really generative to try to consider that if you were going to write like a book about this. But I think it's a fair approach and I don't want to force you to answer it now. My question is about just like feedbacks and time scale. Like, I think this premise that we cannot accept blackouts is a really good one to start from. But we also can't accept in 2100, 800 parts per million CO2 kind of climate apocalypse. And the 30-year timescale is so important for building things and the lifetime of things. But I guess we also sort of lock in choices that may reduce our possibilities for adaptation in the future. So how do you consider these questions of feedbacks and timescales in your work?
Yeah, excellent question. And you know, some of these combustion plants actually have 80-year timelines. So if they're being built out today, we could expect them to be operating at 2100. Okay, so that absolutely for sure. Typical solar array, you know, like a solar panel degrades about 0.5% per year. So really, you know, it basically is going to tail off to below 80% of capacity in like 20, 30 years, right? So they have to be replaced, right? So there's a replacement cost to do that. So I accept your criticism of cop-out. I get it. There's also a cost of geopolitical risk. What does this cost? So we have to include those too. It's just probably not, it would be difficult for a geologist to do work on ethics and human health. I would get it wrong, but you know, we could expand, and we really would like to expand and get the right kind of ethics people to help us think through this. I don't like necessarily put a dollar sign on ethics, like, because ethics it's not something that has a dollar sign, but it's something that really needs to be considered in the equation in some way. So, so to get to your other question, and then you can toss me the mic at me, is that, you know, you're right. I mean, I think that this here will help to guide. If we take that median $90, it's about $90, $92 per ton of CO2, we can see immediately where those cost surcharges are highest. And if we use that part of we use this in the equation, this is why we wanted to include the environmental cost, because those costs are going to get higher. And the higher they get, it basically will help to steer the discussion towards areas and technologies that have lower environmental costs, because it starts to become a higher and higher percentage total. So that's first. The second thing is it will lead to innovation. We try to do we try to look at what's known as demand response. In other words, demand response is when the grid gets under stress, your thermometer in your house would automatically change to reduce the demand. So that's where the demand response comes in. There's a lot of areas of innovation in grid management and in technology management that we haven't yet thought about. And we haven't necessarily thought about or developed because it hasn't hit the right price point. As we go forward into the century, I think we're going to hit those price points, and people are going to see the value of doing this. And, you know, like it or not, we live in capitalistic society, and there has to be a way to operate this with the least amount of government incentives as possible. Because as soon as we start seeing changes in administration, those incentives go away, and it causes this huge pendulum swing that industry can't deal with. Banks can't deal with it because the companies have to get bank loans. The bank's like, oh my God, you know, now what do we do, right? Now our loans are at risk, which means the banking industry is at risk. So this whole house of cards is kind of built on these foundations that we have to, you know, this is what we got. So, you know, we go to war with the army we got, not the army we want. And okay, so let's figure out how to take innovation as fast as we can while we maintain stability and while we maintain price. That's, I guess, how I would respond to that.
Such a complicated problem, and the thoroughness that you all are taking, I think, is extremely commendable. It's a fascinating system. Thank you.
It's really impressive how far you can get that cube. Great.
Right, we have one remote question from Judd Parton. He says, nice talk. Question, how does the ecotoxicity and eutrophication of the solar and wind compare to the toxicity of the semiconductor industry? in terms of orders of magnitude? Comparable, more, less?
Haven't done that comparison to know where that comes in. It's a good question. I don't know. We'd have to look at it, and then we'd have to somehow compare them. Do we compare a megawatt hour to a chip? We have to come up with what's known as a functional unit that we could do a side-by-side comparison between a chip manufacturing, which is a load, versus a power plant, which is a source. So it's probably too difficult right off the top of my head to do this in front of y'all. My guess is that it's going to require a huge amount of material processing to build the chips. And I don't think that that's been necessarily incorporated from an LCA standpoint in any study that I've seen, but I'll bet it's high. And the race is on, right? Do we use AI with all the data centers and the chip centers to reduce, we're going to use machine learning to somehow like manage the grid in a way that reduces the demand faster than the center itself. This is like the great race. And I don't know where that race is going to end up. But the Skynet and the Matrix will figure it out for us.
Yep.
Other questions? We're kind of 3 minutes over, but I'm happy to answer any questions either here. I'm not far. Y'all get my emails or you delete them.
I'll throw a question out
Okay.
to wrap things up, maybe. Because the question of how you put a price tag on some of the environmental toxicity to me is fascinating, partly because it must rely on a ton of assumptions. It's poorly studied. But also I think about, when people sue, there's the pain and suffering part. And so it's not just the cost of the hospitalization or the cost of procedures. So and one could make the argument that, in the future, water might also have an increasing scarcity and cost, and there's a value judgment. Is this for people to survive, or is this for power generation?
Yeah, I mean,
so how do you think about that, or where do you see the biggest challenge in addressing that?
So the value of a human life this is what EPA does. They do it now. They have a whole division of actuarial science. And they say, well, this is the value of a human life in America versus in the Congo versus here or there in dollars. And it's based on what you in this country would generate economically during your lifetime. And so the values change. I mean, this is like bloodless, right? I mean, I don't even want to touch that. And our economists are like, oh, that's really messy and we don't want to do that, right? So now the question is, okay, now the person hasn't died, but the person's gotten sick. Again, we're just, right? Okay, so what's the impact of a person getting sick? And there are studies that are out there that do this. We really have not looked at this. So I don't have a good answer for you because to me, this is outside my system boundary. And now we finally have the numbers where an actuarian or a person who does this would be able to look and say, here's the number of kilograms of PM2.5 that's going to be occurring in this location. And this is the demographics of the communities that live downwind, so that they can do it. Whereas before, we didn't really have the numbers. Now we have the numbers at a system level. I think it's going to be easier to do that. And that was the first part. Did I get the second part? Okay. Yeah. We're not really, we didn't, those numbers, I mean, when I saw the numbers of 2,4-dichlorobenzene, I lost my mind. I was like, there's no way that the numbers could be that high. I mean, so I was like, well, what do you suppose the 2,4-dichlorobenzene equivalent is for 1 ounce of gold? It was like 10 to the 6 tons of 2,4-dichlorobenzene. I mean, the numbers were so astonishingly high that I had a student do an entire report on why are these numbers so high. And the reason is that really, really small amounts of lead and hexchrome and other types of metals, which have an infinite lifespan in the environment, they're relatively speaking, they're essentially their characterization factors, which is essentially a relative ratio between the two and the impact. It's like millions. It's in the millions. So very, very small amounts of lead and chrome and other types of metals that land on the ground has an outsized influence over many other types of chemicals that have a breakdown with daughter products. They volatilize out, they photooxidize or whatever. So there's no there's no, you know, the fate for those metals goes on forever. And this becomes a problem when you landfill, because now you have metals in the landfill that could potentially leach out and reach water for the end of time, forever. And so we still have a lot more to do on this. And so we did reach out to an environmental economist. It didn't work out as well as we would have liked, but we're still kind of working through that.
On that
Thanks,
uplifting
y'all.
note, sorry. Thank Michael again.
Thank you.